Let me see if I can. Can you still see it?
Yes, I see. Can see.
Okay. I'm just gonna see if I can do this in a way where I can still see you guys.
If you have two screens, you can put this window on one screen, one desktop, or this on the and share the other one.
Oh, okay.
If you have two monitors.
Yeah, I do have two monitors. For some, I'm not sure why it's. Let's see. It's for some reason it started mirroring. I'm not sure why. Oh, okay. That seemed to work.
Okay, great.
Great. Cool.
Okay. We can start whenever you are ready.
Oh, okay.
Okay,
Cool.
okay. Okay. People will
Yeah.
join. We also stream it on our YouTube channel, and people can watch us on YouTube.
Okay. Oh, on YouTube. Oh, wow.
Yeah,
Okay.
yeah, yeah.
Cool.
Okay.
Um,
So,
uh,
okay, thank you for accepting our invitation, and we are welcome everyone. We are very pleased to have Professor Marco with us, who wants to give us an inspiring talk about making sense of intelligence, both natural and artificial. And we hope that this talk be something that inspire us, because most of the people that taking our course are engineers and have engineering background, and I think this talk would be one that inspired them to do some interesting research. And thank you for accepting our invite, and thank you for being with us today. Without further ado, we can have your time. Thank you.
Great. Yeah. Thanks so much for having me. Yeah. So I'll be talking today about kind of mainly cognitive science, but really cognitive science in the context of thinking about artificial intelligence and kind of connecting with the things that you probably focused on in this course related to reinforcement learning. And I kind of want to start at a kind of abstract level, which is this question of like, how do we make sense of intelligence? And intelligence is interesting because it's something that both occurs naturally, and also we've more recently been able to actually build systems that seem to have some kind of intelligence themselves. And often, this word intelligence is thrown around to describe the systems that we're creating. And a lot of disciplines have studied intelligence, and we can broadly divide this into two camps. So one is within the behavioral sciences and cognitive sciences, psychologists and neuroscientists have long been studying intelligence, you might say, and learning and so on in humans, in other animals, and what we describe as intelligent behavior or adaptive behavior manifests in lots of different ways, right? So in the development of a child, in how other animals interact with one another, and at the same time, right, more recently, as I said, things that you probably focused on more in this course, um, is the engineering side of intelligence, you might say. Uh, building systems that exhibit certain levels of intelligence, things like machine learning and robotics. And we can kind of broadly think of these things as, on the one hand, engineering artificial intelligence, and on the other hand, understanding biological or natural intelligence. And on the biological intelligence side, the kind of deliverable that we're often interested in is what you might think of as descriptions or explanations of existing phenomena. Whereas on the engineering artificial intelligence side, we are building technologies and identifying design principles for building systems that exhibit some kind of intelligence. But even though we use the word intelligence for both of these things, what is it really that kind of cuts across both of these practices, both of these undertakings, right? Are we talking about the same thing? What does it mean to talk about the same thing? And so I'm going to kind of talk at a high level for the first part of my talk about this relationship between understanding biological intelligence and engineering artificial intelligence. And so I'm giving a talk today titled "Making Sense of Intelligence, Both Natural and Artificial," and to kind of walk through an idea here. I want us to kind of imagine uh, a world where, instead of giving a talk on making sense of intelligence, both natural and artificial, I was actually giving a talk on making sense of hydraulics, both natural and artificial. And bear with me, this will make sense in a second. I want you to imagine that, instead of talking about this abstract concept of intelligence, I was actually talking about, hydraulics. And, I might have started out this talk by saying, okay, there are different types of hydraulics. There's both natural hydraulics, naturally occurring hydraulics, things like, the way your heart pumps blood, the way that, lava flows in a volcano, the way that, other animals kind of use hydraulics for propulsion, like an octopus or something like that. And then there's also artificial hydraulics, hydraulic systems that people have built, like dams and plumbing and engines and so on. And you might think, oh well, that's kind of weird. I guess both of these things are related, but they seem pretty different. But actually, if you kind of take a step back, there's a whole kind of field. There are many fields and kind of theories for describing both of these kinds of phenomena, both naturally occurring hydraulics and artificial hydraulics, and namely fluid mechanics, right? And so, we have this kind of like rich mathematical theory that kind of cuts across both phenomena found naturally in the natural world and phenomena that occur that we've built ourselves, and we've kind of leveraged our understanding of how things occur in the natural world to build them ourselves. And the mathematics both allow us to understand what's going on, as well as build simulations of processes, and both artificial and natural, and better understand them and predict what they'll do when we build them. And so we can kind of think. So I kind of want to, I was using that example to kind of illustrate that we can have both natural and artificial versions of phenomenon that are connected to each other through kind of overarching principled theory. And in the context of intelligence or adaptation, there are roughly, broadly speaking, two ways in which people often make sense of intelligence in this context. And these kind of fall into two camps. So one is kind of a rational approach, and the other is a kind of computational approach. And what do I mean by this? Well, when I talk about a rational approach, I don't necessarily mean, like acting rationally according to like a certain prescription, what I mean is kind of understanding, what is the rationale of a system? What problem is a system that we are observing solving? And these are often described as functional explanations or normative explanations. I'm just going to use the term functional for now. And these often come in the form of, a problem statement a problem statement that's at play, and formalized in terms of something like utility functions. Whereas, while on the one hand you have rationales for explaining it, you can understand a system in terms of its rationale and the problem that it's solving. You can also understand a system at a more mechanistic level in terms of the kinds of computations it's performing or what it's performing those computations over. And rather than asking the question, what problem is a system solving, you're asking the question of what is this system? How is the system finding a solution to the problem, or what is it doing? What does it use to find the solution to the problem? How is it implemented? And these are often described as mechanistic explanations or algorithmic or implementational level explanations. And the type of thing we end up with are things like algorithms and search strategies. And there's a long history in cognitive science of kind of thinking about these different types, and not just cognitive science, but a lot of the sciences, and thinking about these different kinds of explanations, thinking about things in terms of, okay, what is the rationale for something we observe versus what is the kind of underlying sequence of computations that underlie what we've observed. And so most famously, David Marr talked about this when kind of thinking and theorizing about vision and studying vision in the 80s. John Anderson also has written a lot about this. In particular, he has this great book, The Adaptive Character of Thought. And then, as I said, this is not just in cognitive science, but also lots of other fields kind of take this perspective. So, for example, in pathology, which is like the study of animal behavior, oftentimes they need to kind of be clear about distinguishing between, okay, are we explaining like why a behavior is observed, why did it evolve, versus what's actually kind of leading to that behavior in a more proximal sense. This is often described as ultimate versus proximal explanations for something. And to kind of make this more concrete, in the context of, say, psychology or neuroscience, we can ask, if we have our visual system, and we can understand the kind of underlying mechanisms that lead us to form, an internal representation of something in front of us. And so you might try to understand, say, given that light is hitting the retina in a certain way, how is that kind of activating certain patterns of neural activity, or how is that leading to, activity in the optic nerve? How does that later lead to activity, patterns of activity in, the visual cortex and higher parts of the visual cortex? And we can understand vision at this level of, okay, this happens, then this happens, then this happens, and then this happens. But mechanistic explanations are often not able to give us everything we want. And so to give a good example of this is kind of understanding what's going on in, say, optical illusions. So this is a very simple optical illusion where you can see there's this orange dot that's going back and forth, and then we add another dot. We add a few more. Right. So, okay, at this point, you can see that the dots kind of form a circle, and I'll play it one more time. Initially, so the dots are just moving in a line, linear motion, making linear motion back and forth. But as you can see, as you add more dots, they seem to form what looks like, at some point, things transfer over to, oh, I'm not just seeing a line go back and forth, but I'm seeing some kind of polygon kind of seeming to like rotate around the outside of this, or the inside of this circle, this larger circle, and then eventually the whole circle, even without that orange line in place, right? And so you might ask, well, okay, this is an interesting visual phenomenon, right? This is an interesting perceptual phenomenon, and there are many other types of optical illusions and visual phenomena like this. And a mechanistic explanation isn't necessarily going to give us what we want in terms of explaining, why did that happen? Why is this? Why do people perceive this? These kinds of explanation. Another type of explanation you could have for this type of phenomena is a more functional explanation, right? Why do we see this? Why does this like pattern uh, of of dots moving back and forth on a line in a particular way suddenly form and suddenly seem to be perceived as a coherent object and circle rotating around another circle, rotating inside of another circle. And a one explanation for this is that, well, the visual system is actually adapted to not just perceive dots moving back and forth on a line, but actually pick out from incoming visual data what objects there are in the environment, right? And so we can think of this, for example, in a Bayesian framework where you observe some data, some images, and you have to kind of invert a model of how objects lead to images on your retina, and then figure out, oh, what is the object out there in the world, right? And so vision is a very good example where it's extremely useful to be able to think about, okay, what is the function of vision in order to explain why we perceive things in a certain way, why we observe certain phenomena. And in the case of the visual illusion, because again, we're not always perceiving dots moving around, we're not interested in dots moving around. The point of the visual system is to identify coherent objects in the environment and respond to them, so that they can be responded to. To this kind of explanation is kind of key for understanding what's going on. Okay, so those are examples of rational versus functional, rational versus mechanistic explanations for a phenomenon like vision. But in my work, I'm very interested in functional accounts, not only of perception, but of higher level and social cognition. The kind of main point I think that's key to realize is that although natural and artificial intelligence can have very different mechanisms, so for example, in the case of visual illusions, when we are observing things in the environment, that's like implemented in neurons and some algorithms in our brain. Whereas if we were to try to implement a system, an artificial system that would be implemented in a computer, those are different mechanisms, underlying mechanisms, and maybe even different underlying algorithms operating over those implementations, but they can share the same function, namely detecting objects in the environment, right? And in the case of perception, these things are fairly clear cut, right? Often it makes a lot of sense to think about, there's an object in the environment, we get an image, how do we invert that, right? It's kind of, how do we form an accurate representation of reality? It's kind of, the kind of first order function of perception. Whereas in, say, higher level and social cognition, it's actually less obvious what, the function of these various cognitive capacities we have are. And even in the case of perception, computational theory is very useful, even though often it's a very well-defined, we kind of come in with good intuitions about what the function of vision or the function of perception is. Still, computational theory there is very useful. In the case of higher level and social cognition, arguably computational is even more useful because these functional explanations are not obvious as they are in perception, and maybe computational theory is unavoidable in this case. And so this is one of the reasons why a lot of my work has engaged with reinforcement learning and work in AI, and kind of bridging these two things. These functional accounts of higher level and social cognition really allow us to kind of bridge both work in artificial intelligence and reinforcement learning and cognitive science. So that's kind of like the big picture idea of what I'm talking about today, which is that, at this level of functional or rational explanation, there's actually many opportunities for conversation and exchange of ideas across both AI and cognitive science and psychology. So in the context of my own work, and what's probably most relevant to this course, I've been very interested in key aspects of how people solve problems, right? And when we are, and there are many aspects to how someone solves a problem, and there are many examples of solving problems. So navigating to a location, even in a city that you're familiar with, taking the subway is a type of problem solving. Deciding what to cook for dinner is a type of problem solving. How to cook it for dinner is a type of problem solving. Playing chess is a type of problem solving. And in particular, a key part of how people solve problems is that they reason about what's going on. They form a model of what's going on in the world, and then plan and best respond within that model. And this idea that people are planning and kind of forming internal representations of the world in order to act in the world. It goes very far back in psychology. It goes back to work by Edward Tolman, who was very interested in how do simple animals, how do mice plan in a maze, for example. In the 1960s, George Miller and colleagues were interested in this idea of, okay, how do plans structure behavior? How do people seem to have this internal representation of what they're going to do, namely their plan, and that has an influence on what they end up doing. And then most famously in the 1970s, Alan Newell and Herb Simon kind of explored this idea in formal terms and developed a computational account of what it means to solve problems. And this computational formal account has really played a big role in how we think about planning and problem solving in humans, as well as kind of laid the foundation for thinking about it and building it in artificial systems. The kind of key idea behind the Newell and Simon paradigm is that we can kind of think of planning and other types of sequential decision making as involving basically two components. So the first component is having a representation of a problem, right? And so, the classic example is thinking about chess. So in chess, you have a representation of the objects on the board, of the pieces, and how they move and how they interact with one another. And you have a goal, which is to capture or checkmate your opponent's king. And given this representation and rules for transitioning between states as a result of actions, you can build a tree of some kind and search for actions to take in that tree. You can kind of move down the tree and select, see what would happen, imagine what would happen if you search for different actions. And so this idea of doing some kind of tree search has been very influential, not only when thinking about planning, but also thinking about sequential decision making more broadly. So within reinforcement learning, we often also think about things in terms of, okay, there is we have a Markov decision process that describes the transitions in the task and how we move around as a result of actions. And it also describes the reward function or the goals of the task, what we're trying to do. And so given an MDP, given a Markov decision process, then we run our RL algorithms on that Markov decision process to get an optimal value function or an optimal policy, or near optimal value function or near optimal policy. And we can kind of think of this, so I'm going to call this way of thinking about the relationship between task representations and finding a policy as the standard model of planning, of which heuristic search is a good example. Heuristic tree search is a good example. But when we think about how people solve problems like chess, or really any problem requiring sequences of actions, this framework is actually a little has some kind of like inconsistencies, or it doesn't quite fit perfectly. And that's for a couple of reasons. In particular, um, in the Newland-Simon kind of standard model of planning way of thinking about things, the way in which we represent the task is fixed, right? So we get our MVP and then we run our algorithms on it, our search algorithms on it. But within psychology, there's actually a very large literature showing that people don't just represent tasks in this kind of fixed way. And so, for example, work on insight problem solving, work on analogy, in which you kind of take your representation of one problem and kind of map it onto the current problem, and that helps you solve the problem better. Work on analogy has kind of affected. It kind of shows that we're not just representing a task in a fixed way, or that the task representation matters. And work on expertise also shows that experts kind of seem to represent tasks differently than novices. An expert chess player represents the task differently than a novice chess player. And this observation that experts and novices seem to think about tasks in a different way, it actually goes very far back. Newell and Simon were aware of this even when they were developing this approach. In their book, they cite work by these Russian psychologists who looked at how do expert chess players look at the pieces on the board, right? And so that's what you're showing, what I'm showing you here on the right. These are the kind of movements of an expert chess player and where they tended to look on the board on the left. And what you can see here is that it's not as if the expert chess players are kind of encoding the whole board and then chugging through what to do. They really seem to be focusing on very specific objects in the environment, right? And so if we were to actually kind of paint a picture of what's going on here, they are, if we were trying to like estimate based on the eye movements, what they were looking at, what they spent the most time looking at, they're looking at very specific pieces, and presumably they're reasoning about interactions between a subset of pieces, this subset of pieces. And again, as I said, Newell and Simon were very aware of this question, but they kind of like bracketed that, but it left open this big question of, okay, how do people come to the representation of tasks in the first place? We know that people are forming a representation separate from the kind of underlying true dynamics of the underlying true causal system that they're looking at, but how do they come to that representation, right? And so in the work that me and my colleagues have done, we've been interested in this question of, okay, how do people represent tasks? Can we understand this in a more principled way? And the way that the proposal that we have is that people are basically constructing what we call value-guided construals, and I'll talk about what that looks like more concretely. To study this, we didn't use chess. We looked at people navigating through mazes like this here. So people would get a top-down view of a maze. It's basically a grid world where you control the blue dot in the lower right there, and you're getting to the goal in the upper left. And on each trial, you always had this cross in the middle, which represented these fixed walls, these black fixed walls, and then you had these obstacles, these blue obstacles that changed on each trial. So within a trial, they were fixed in location, but they changed across mazes. So they were just rearranged to construct a new maze. And your goal is obviously to get to the goal state in the fewest number of steps possible, and avoid the obstacles and walls. And so a trial looks like this, where the trial begins with the walls in the middle, and then when you're ready, everything appears, and then you navigate to the goal. And then at the end, as I said, we were interested in how do people represent the problem, right? How are they thinking about it? And so in this first experiment, we asked people, okay, how aware of each obstacle were you while you were doing this task? And they would answer on a scale, and we recorded that. And the data looks like this. So the first thing is that, so this is a plot of what people are doing in the task, like how they're moving. And as you can see, people are very good at this task. It's a very simple task. They look at the maze, Again, this is a top-down view of the maze. They look at the maze and then they navigate to the goal. They encode it and then think about what to do and then do it. But as I said, we're interested in the representation. And so these awareness scores become very important for that. And what I'm showing you here is for each obstacle in that particular grid, what the average awareness score was for that obstacle. And as you can see, there's like a pattern here in terms of what people are reporting, paying a lot of attention to when they're doing this task. And so what we're trying to understand is, okay, why are people paying attention to this combination of objects in the task? And okay, so that's kind of the task and the data that we are trying to explain. And so we can ask, okay, well, how would like the standard model of planning think about this approach? Well, in the standard model of planning, you have your task, and then you do planning over that task, and then you take an action. Quite simple. And so it would look something like this, where, okay, there's the task out there in the world. You do planning over that task. So what I'm showing you here is the result of a planning algorithm that kind of like expands a graph from the start state, and then does planning over that graph to figure out how to get to the goal. But you can imagine lots of other algorithms that do planning. You can imagine doing something like reinforcement learning over this internal representation of the task. And then given the result of that, you act. You take a sequence of actions to get to the goal. Our proposal is that there's still the task out there in the world, you're still forming a plan and you're still taking actions, but in between or in parallel with doing the planning process, you are forming a representation of the task, which we're calling this task construal. It's how you construe the task in order to plan. And it looks something a bit more like this, where you have your true task out there in the world, but you take the true task and you form a simplified representation of that task, which I'm showing here. And so here, the grayed out blocks are details or obstacles that are being ignored or left out of the task representation, and the blue ones are the ones that are still there. And so you have this task representation, this task construal, and then you do planning over that task construal, that simplified object. And then you have a plan, and then you can execute, or you have a plan, you get a plan, you do planning over it, you get a plan, and then you take actions based on that plan. And so, yeah, so the key thing here, again, is that there is this process happening of actually taking the task in front of you and kind of boiling down its details into a simplified representation that you can do planning over. So how can we even think about this process? Well, the kind of overarching idea in this work is that this process of construing a task in the world in order to plan in it and take actions in it it's a value guided process. It is a process of choice. And when we think about choice processes, we need to ask, okay, what is the utility function that we are optimizing here? And so our proposal kind of comes down to a proposal about the form of this utility function. And in particular, we define this value of construal, which I'll explain more in a bit, in terms of two components. So one component is this notion of behavioral utility, and the other component is the cognitive cost. So, okay, what do I mean? What do all these pieces mean? So the first thing is that, what do we mean by a construal? How do we formalize this notion of a construal? Well, what we assume in this situation is that you have your task, and then given this like input task, that task is parsed into a combination of local interactions or cause-effect relationships, interactions between the agent and objects in the environment. And one object that we consider here is this notion of the walls in the middle, specifically the possibility of crashing into the wall and not moving. And we also consider each Tetris piece here as a kind of local interaction, right? Which gives us, this set of local interactions, this kind of parsing of the scene in front of you into objects and interactions between objects. And then we assume that you can select a subset of these interactions. So for example, you can select the cross in the middle and then some subset of these objects. And then those components, those pieces are kind of bound together uh, into a transition function, the simplified transition function that we're calling a construal here. And the key thing here is that we're actually kind of constructing a new MDP from the old MDP, kind of performing a type of abstraction of the MDP, right? And we haven't actually done planning yet. So we have this new simplified MDP over here on the right, this construal. And given this construal, we can then do planning over it, right? And so this behavioral utility term then becomes a function of the plan that we compute with this construal. So what do I mean by that? Well, okay, let's imagine we have our construal here on the left, and then we compute a plan on it. So given the MDP on the left, the optimal plan looks something like this, where you go up and to the right. But the problem with this plan is that if we were to take that plan and then put it in the actual world and execute that plan would do things that we didn't quite expect. It would crash into this wall here, for example. And so actually, the utility of this computed plan is actually quite low. It doesn't actually help you get to the goal, right? And so the key thing here is that we have our simplified MDP, our construal, and then we have the real MDP, and we get a plan from the construed MDP, and then put it on the true MDP and see what happens. And that's how we get the utility of the computed plan. Okay, but of course, we're interested in not just one construal, but this set of possible construals and figuring out which one is good. And let's say we were to add in this object here, replan, and then execute that plan. Well, this plan actually has a good utility, right? Because it avoids the objects and gets to the goal. Okay, so that's the behavioral utility component of this. But then we can also ask, what is the complexity of a construal, right? What is the cost of a construal? And this is particularly important for thinking about how humans are solving problems, because unlike machines, we can't add a computational power to ourselves, right? And so a big part of what's happening when humans are solving problems is this need to manage the cost of doing computations in order to solve a problem. And so how can we think about this cost? Well, as I said, here we're thinking about a construal as a representation, and we can ask, okay, what is the complexity of that representation? What does it take to represent that MDP in our minds, and then do planning over that MDP? And to quantify this, to give a number to the complexity of a construal or simplified MDP, here we just look at the number of objects that are at play, the number of objects that are included in that construal. It's a very simple measure of complexity. There are many ways to think about complexity that we're exploring, but in this project, we focus on this very simple formulation of complexity. And so from this perspective, this construal over here on the left is actually not ideal, right? It kind of has extraneous details that don't that aren't necessary for solving the problem. In particular, there are these two objects here, which if we were to remove them and then plan on the task, we would get a new plan. And that plan also has a high utility. It also get us to the goal without crashing into the objects. And so this construal has a high behavioral utility, and it also has a low cognitive cost relative to the other construal we were considering. And so this is actually the optimal construal for this particular maze. Okay, so that's kind of the computational model, the computational theory that we developed in order to give an account of the types of representations that people form. But we can ask, okay, do people actually form these types of representations? Do people form these kinds of optimal construals as we've laid them out? Are they optimizing? Are they solving? Is this the problem that they're solving? And we can first look at the predictions of the model. So here's the maze that I showed you before. And then if we compare that to people's actual responses on that experiment I talked about, we can see, at least visually here, that there is a correspondence between these two mazes. And here are two other mazes from our experiment. As you can see on the left, people seem to pay attention to the objects on the left of the maze and less on the right, consistent with the model. And then on the right example is a bit more interesting because here the objects are kind of the things that the model predicts will be paid attention to are not right next to each other. They're not all right next to each other. And that seems to be reflected in people's awareness responses on the experiment. Okay, so this is kind of a visual comparison. For a more quantitative comparison, we can at a very coarse grain level, we can look at all the objects that were predicted to be ignored by the model, and then compare that to what people reported on the task in reality. So as you can see here, obstacles that were predicted to be ignored, people tend to assign a lower awareness score to, and conversely, obstacles that are predicted to be included in a construal that are predicted to be attended to tend to lead to a higher awareness score. Okay, so that's, that was the first experiment we ran. But I want to kind of give you a sense for what is actually going on in this model and kind of the particular things that it predicts that is maybe different from a simpler model. And to do so, I want you to imagine that you are in a place like New Orleans. So New Orleans has this big lake next to it, and there's this long bridge that goes across the lake that people take to get to work very often. And I want you to imagine that you're on the south side of this lake, and you need to get to the north side. And on a normal day, you would just cross the bridge to get to your destination. Very simple. It's the shortest route. But now I want you to imagine that one day you're watching the news and you find out that there's a truck blocking the bridge, and it's blocking all traffic. And now you can't get across the bridge to get to your destination. And instead, you have to take this other route that goes all the way around the lake to get to the goal. What's interesting about this example is that if you intuitively think about it, even though the truck is really far away from the path that you ended up taking, it's obviously very relevant to having taken that path. And if we were to actually put a person in this scenario and ask them what to do, and then ask them, okay, were you thinking about the truck? Was the truck in your representation of the world when you were making a plan? They would most definitely say, yes, the truck was in my representation. And that's kind of interesting because, again, the truck is very far away from the path that you ended up taking. And moreover, you're not really thinking about other things that are near the truck, like the cars that were, in between your start location and the truck. You've kind of constructed the simplified model in a way that doesn't have like local correlations necessarily. And so we developed, and so this example kind of motivated us to develop a version of these mazes where there were kind of trucks of a certain kind in the maze. And in particular, if you have this kind of maze, and then we have people, take a sequence of come up with the optimal policy and get to the goal, they would do something like this. And there's several different kinds of obstacles here. So there are some obstacles that are obviously going to be very relevant to the path that you ended up taking, that are very near the path. So these obstacles here. But then, like the truck, there are going to be obstacles that are far away from the path, but because of the way that they affect the plan that you construct, they are very relevant. And then there are obstacles that are irrelevant to the path that you ended up taking. So these ones right here, for example. And so we ran a new experiment with these types of mazes. We ran a couple of versions of this. One version, instead of using the self-report measure from before, we had people give their accuracy. What we had people do was after they did the maze, there were two changes, actually, two big changes to this version of the experiment. So the first is that rather than having people see the obstacles the whole time they navigated, the obstacles, once they started moving, they would become invisible. They were still present, so they would still block you, but you couldn't see where they are. And so what this kind of encourages people to do is really do all their planning at the beginning of the problem. And kind of gives us a cleaner measure of the kind of representation that they're forming. Um, the second thing we did was, rather than having people just tell us which they paid attention to more, we gave them we took all the obstacles off the board, and then added one obstacle back, and then added a distractor obstacle that wasn't overlapping with any of the other obstacles, and asked them, okay, which of these was in the location that you just, or sorry, which of these was in the maze that you just did? And so you have these two. So there's a right answer here. One of these was actually in the location. And what that gives us is both an accuracy score as well as a confidence measure. So we ask people which one was it? They say which one. They're either right or wrong. And then we ask them, how confident are you? And they give us a confidence score. Okay, so we ran this experiment, and here's just a refresher of the types of obstacles in this setup. And if we look at people's accuracy and confidence in doing this type of task, ignore the confidence for a second and just look at the accuracy. So if you look at the accuracy, what I've done here is I've color coded the responses here based on whether the obstacles are relevant or irrelevant according to the construal model. So whether the construal model predicts you'll pay attention to them. And what's interesting is that, as you can see with accuracy, if the model predicts that you're going to ignore something and it's irrelevant, then it has a lower accuracy. And if it predicts that you are going to pay attention to it, it has a higher accuracy. So that makes sense. But what's particularly interesting is that there is this division based on relevance, based on the model's predictions, separate from whether things are near or far, right? And so what that tells us is that people are constructing a representation that is not just necessarily taking into account things that are close to one another, but actually kind of picking out selectively in a much smarter way what is the relevant pieces of the environment that we need to be considering when solving this problem. Okay, so that's kind of the basic idea of the main line of work. There's a couple of ways in which there are a couple of concerns you might have about this story that I'm telling, right? That people are kind of going around the world, forming representations of the world in this very intelligent way, in which they construct a model, plan in it, construct a model that has all the relevant information, and that when planned in gives you a good plan, right? One concern is that actually what we're looking at is not the result of this kind of value-guided construal process, but really a side effect of other kinds of processes, of other kinds of planning processes or perceptual processes that we already have studied a lot. And then the other concern that you might have is, well, this sounds like a very complicated process, and in a way, you kind of have to the way I've stated this problem. You kind of have to know the answer in order to get the answer, right? There's this kind of chicken and egg problem going on. How do you come up with a representation that gives you a good plan before you know what a good plan is, right? In order to come up with a good plan. And so that this kind of is the question of what is the computational feasibility of this approach? So I'll talk very briefly about this first concern, and then maybe focus a bit more on the second concern for this audience. But the basic idea is, okay, is construal a side effect of other stuff? So our claim is that this value-guided construal process looks like this on the right, and that we are actually probing the construal process itself when we say do the memory probes, right? But alternatively, it might be that this process of planning is just something more like the standard model that we've talked about, and there's a byproduct, like this construal process, this construal that we seem to be measuring is just a byproduct of that. And so to get at this question, we actually looked at a couple of different alternative algorithms that basically operate on the full MDP without constructing a simplified MDP. And so just as a point of comparison, the value guy construal model predicts that you'll pay attention to the ones in blue and ignore the ones in gray. But we can actually look at other types of RL algorithms or planning algorithms that operate on the MDP and ask, okay, well, if we were to run those algorithms, are there certain parts of the state space, are there certain obstacles that they tend to encounter a lot? And so one of the algorithms we looked at is this real-time dynamic programming algorithm, and RTDP does something like this, where it does rollouts from the start of a trial and then kind of iteratively builds out a more accurate value function. And so this is just what it looks like on forums. And the key thing, another thing here, is that RTDP takes a heuristic, so we can give it a heuristic so that it isn't starting entirely from scratch. And the heuristic we gave it here was just the distance to the goal, the Manhattan distance to the goal. Okay, so that's on something like 4 rooms. Now what happens when we put it on a task like this? Okay, so if we put it on this type of grid world, this type of maze, what you see is that it first tries to explore what it thinks, according to the heuristic, is the shortest path on the right. But then it realizes that it takes it a while to realize that the heuristic is actually bad, and it has to unlearn it. And then it begins exploring along the more optimal route, and eventually it constructs, it figures out what the path is. And so the key thing here is that in order to figure out that it needs to go up and to the right, as opposed to right and then up, it needs to first propagate the values. It has to unlearn the heuristic values to the right before it goes up, right? And that requires interacting with these 2 objects on the right, these 2 objects right here a lot, right? As you saw before, it was kind of hanging out here for a long time. And so what we can do is, after running this algorithm, we can ask, okay, what did it interact with? What objects did this algorithm, when it was run, bump into a lot? And so what we did was we counted the number of times it bumped into each of these, and then we took the log of that, because that led to a better measure. And what we find is that, as I was saying, you need to interact a lot with both objects on the right in order to calculate the optimal plan here. Okay, so that's a trajectory-based approach, kind of very RL-like approach. But you might say, okay, well, people are actually smarter than just running RL in their head. They're not just running simulations in their head in this really naive way. They have a representation that they can kind of jump around, and this is exploited a lot in planning literature by using backtracking. Algorithms like A star can do this. So we then we ran A star, a variant of A star for MDPs on this task, and so this version kind of creates a graph, kind of explores the state space and creates a graph, and then does planning over that graph. And as you can see, this algorithm also has to explore to the right, kind of expand the graph to the right before it starts expanding the graph upwards and then to the right. And we can look at, okay, where did this graph end up hitting the different obstacles? And as you can see, even this graph-based approach, which is smarter than the trajectory-based approach, needs to explore the obstacles to the right in order to come up with the optimal policy. Again, this is all because it is operating in the fully described state space, right? The fully described MDP, and not a simplified MDP. Of course, we could run these algorithms on a simplified MDP, but the idea here is that, okay, if we were to run this on the full MDP and people were not simplifying the MDP in an intelligent way, this is what would happen. Okay, so these 2 algorithms are really kind of like algorithmic, or these 2 models are algorithmic approaches. We can also look at various perceptual things, like the distance to the bottleneck, the successor representation, distances to the path, distances to the goal, and so on. And the key thing here, though, is that the only model here that is adapting the representation and not just performing some kind of executing an algorithm on the fixed representation is the value guided construal model. All of these other ones assume it's a fixed representation and can do very complicated things on that fixed representation, but are just assuming the fixed representation. Okay. So we wanted to compare this to the data, and so we did. I'll go quickly through this. I know I'm close to time. We fit a single model to everything using all of these as predictors, and then for each one we removed each one, refit it, and then we compare the lesioned model to the global model, and that tells us how important was that model for explaining what people did, even taking into account all the other models. And so that's what I'm showing you here. So the change in fit, a large change in fit, means that it was a very important model for explaining people's behavior. If we look at the value guided construal model, it leads to a very high change in fit. These other models lead to a lower change in fit. Okay, so this kind of addresses this first concern. What about the second concern? What is the feasibility of this value guided construal process? Well, I'm just going to very quickly sketch out the general approach, the general idea here, which is that we can think of this value guided construal process as an optimization process in and of itself, right? And so the key thing is that construal is actually a kind of meta optimization, similar to meta learning, where you are optimizing the inputs to another optimizer, namely the planning algorithm that you're dealing with, right? You're choosing an MDP for a planning algorithm to then optimize. And so we can think of this as a search problem or as an optimization problem. And the way we're currently thinking of this and exploring algorithms for is you have a space of construals, and they're kind of bounded on each side by, one is the empty construal, a construal that has none of the objects, and then the full construal, which is a construal that has all of the objects. And in between, we have this lattice of different construals that contain different numbers of things in them. And one way you can think about this, what we're optimizing in this space, is a kind of combinatorial optimization, which is in general very hard, but can be sped up by using heuristics or treating it as a kind of search process. And so, for example, inside of this lattice is this optimal construal, which is kind of the construal that minimizes the value, maximizes the value. For example, you could start from the empty construal and do something, even if you do something very naive, like breadth first search evaluation, you kind of add each construal one at a time, get the optimal policy for that, and then keep going. Even if you do that, you can save a lot of computation, right? And so we're currently exploring various ways to make this process faster, heuristic, essentially doing a kind of heuristic search in the space of simplified MDPs. Okay. So I know I'm at time, so I'll go quickly. I'll kind of jump ahead through this. One kind of direction that we're very interested in is looking at how do people kind of form representations heuristically to solve a problem, and the kind of high level takeaway is that this notion of cognitive cost can kind of extend over temporal windows as well, and lead to kind of a stickiness in how we represent problems. Okay. So that the line of work that I mainly focused on for this talk was thinking about basically how do cognitive costs, how do people solve this problem of representing a task in a way that they can then efficiently plan on. But another big direction for my group is not just studying how do people solve problems individually, but actually solve problems collectively or interactively. And I think this is actually quite important for thinking about human uses of artificial intelligence, right? So as human beings, we often much of what we do is learned from other people through communicative interactions, right? Especially in childhood. And so uh, a lot of the work we've done looks at how do we model, how can we think about the computational processes that are happening when during teaching, when we are communicating with one another, particularly in embodied environments where maybe language is not sufficient for conveying how to do a certain thing, right? Like teaching someone skills, the skills they need to build a little tower or to code or things like that. And this is a problem that is relevant for how humans are going to interact with machines that we need to communicate with. So how can we get them to understand our mode of communication, and then also for them to communicate with us, right? How can they more effectively communicate with us? And in many ways, the need to communicate and the need to solve problems individually uh, form the basis, form the foundation for joint problem solving, right? How do groups of people solve problems? And I know you've talked, I know Peter Stone came and talked, and we are thinking a lot about how do we kind of take these ideas from multi-agent reinforcement learning and adapt them for thinking about how humans interact with one another. And how various kinds of human biases and human tendencies when solving problems kind of affect what the joint solution is that humans come up with to a problem. Okay, so there's a long history, as I said, of interaction between artificial intelligence and psychology. I really like this quote from Amos Tversky, kind of a big name in psychology, who said, "My colleagues, they study artificial intelligence. Me, I study natural stupidity." Right? And uh, and so I pretty strongly believe that in developing AI systems, we should think about, okay, how do we use them to complement our so-called natural stupidity um, uh, in a way that can allow us to kind of overcome our cognitive limitations, for example. Okay, so just some final thoughts. I know we're at time. Um, uh, as I started out, the kind of big picture takeaway, I think, in thinking about the relationship between cognitive sciences and artificial intelligence is there are many different like levels of explanation in thinking about both natural and artificial intelligences. And one way in which we can kind of share insights across these two endeavors is through thinking about, okay, rational explanations. Okay, what is the function of a system? How can we formalize the function of that system? How does that explain uh, phenomena we see in the world, behavioral phenomena we see? And how can that inform the development of artificial systems that have similar function? And then I talked a bit about task representations as an example of this approach of thinking about, okay, how can we frame the formation of task representations as a problem that's being solved? What is the problem that people are solving when they are going around the world trying to decide what to pay attention to? A big part of that is, okay, we pay attention to things that in combination lead to representations that lead to good plans, right? So it's kind of backing up from like, I need a good plan, I need a good behavior in the world, to how do I come up with a good representation that will give me a good plan? And that's essentially the idea behind our proposal for value guided construal. And finally, I talked very briefly about how we can think about another point of interaction between cognitive science and artificial intelligence is using these systems or using insights from human social intelligence to inform the development of social intelligence in machines. And then finally, informing how we can design interactive ML systems that really complement our cognitive limitations. Okay, so I want to thank my collaborators on the work I presented: Carlos Correa, David Abel, Tom Griffiths, Michael Littman, and John Cohen. And I want to thank you all for taking the time to listen to my talk. And I think we go into questions now.
Thank you, Professor, for your wonderful talk. Yes, we are opening for the question, and Please raise your hand if you want to ask question, and I give you the mic access. Okay. Okay. So until people prepare the question, I have a question. I was wondering if the example that we give about the hydraulic, natural hydraulic system and artificial hydraulic system, I was wondering what are the instances of the intelligence that we see on the in the nature, natural intelligence, that we still cannot explain them with the laws of thoughts that we know, with our understanding of intelligence. What are those examples that could inspire us to, I don't know, try to understand them or think what's going on in them? Can you give us some example about those things? Thank you.
Yeah, absolutely. Yeah, so for one of the most interesting questions from my perspective is just how do people do so much complex behavior uh, given such limited resources, right? Such limited data to learn from, and two, limited computational and fixed computational capacity, right? So our best AI systems, our most impressive AI systems, they either take a ton of data to train, or they take a ton of compute to to come up with a solution, or both, right? Our most general AI systems require a ton of resources to solve problems, whereas humans, the human brain runs on like the equivalent of like less than a light bulb of electricity, right? To do what it does, and it's so much more general. We're much more general problem solvers than any of these super uh, high resource systems. And of course, a lot of it is like we can optimize those systems and so on, but fundamentally they're operating in a regime that is like so much in a much an order of many orders of magnitude more data and compute than humans do. So that's one area in which I think we don't understand. There's something about natural intelligence that we haven't quite figured out with artificial intelligence. um, uh, a related thing is, just the generality of natural intelligence, like humans. We can solve many different problems. Uh, there are certain systems that some systems, like large language models and so on, are quite general now, but they don't solve problems as both generally and reliably as humans do. So there's a lot to figure out uh, there. And then I would say another big area in which we don't entirely understand how humans do it, uh, and we also can't yet do it in machines, is social intelligence, or kind of collective intelligence, right? So if you look at, like, human beings have somehow figured out through a combination of individual problem solving and like cultural accumulation of insights, have figured out how to solve lots of complicated problems, right? No individual person could go from like uh, agriculture to like flying to the moon. And so we've somehow managed to do that. Again, it's related to this question of how do we do so much with such little resources. But thinking about how like groups of people are kind of large groups of people, or medium to large groups of people, kind of embody a kind of collective intelligence, I think is something that we don't totally understand, that we could get insights from.
When I think about this problem, I see it, many of it because of the evolutionary process that we go through on, and a lot of it is optimization over generations. And I was thinking, do you think we can simulate that process? It seems to us that we have some foundation models and we have some algorithms that we didn't really understand. We don't know how they work exactly. We're trying to understand them through cognitive science and neuroscience. Is there a way that we can simulate that evolutionary process and the multi-agent nature of that evolutionary process, that we cannot optimize or somehow use some heuristic to get to those core foundation models and learning algorithms that can lead us to the way that we are, the intelligence that we see around us and go beyond it to super intelligence? Do you, that's a big question, but I want some ideas. What do you think could be the way forward to get to that?
Yeah, yeah. I mean, I think I don't have the answer. I don't quite have the answer myself. I think you guys have to figure a lot of that out. Um, yeah, so I do think there is a question of is it all just optimization over just a general function approximation, essentially? Like, or do we need more are there more constraints? Do we need more constraints or priors or inductive biases to get anywhere? Um, yeah, I think it is an open question how evolution combined with learning, combined with reasoning, leads to something close to general problem solving ability. One area that I'm very interested in is how do these almost like different levels of optimization interact with one another to allow us to get more from less, right? So evolution is it's not just that there's a single optimization process. There's like levels of optimization processes that are at play, almost like a hierarchy of optimization processes. And yeah, I think so. That's a direction I think will be key for understanding how we get to general problem solving ability of some kind. Um, I think that's part of the solution. Uh, yeah, I mean, I think a lot of it's going to just have to be trying out different combinations of things, and a lot of it is honestly just kind of conceptual clarity on like, okay, what is the problem that's being solved at different points in this optimization. Um, yeah, yeah. So unfortunately, I don't have all the answers.
Okay, thank you. And I have another question. What do you think about this current wave of AI that with big giant prediction machine using all the information that is available in all the different modalities and try to use some reinforcement learning on top of it to explore a little bit more and somehow define reasoning and add architectures to find out some new things. What do you think? How do you see this current wave of AI, and how do you see its limitation? And what do you think we have to focus on if you want to see 20, say 20 or 30 years ahead? And what do you think is missing in this wave of AI that is right now popular, AI agents and doing optimization with different kind of ways over these foundation models?
hmm hmm Yeah, I mean, so I definitely think the current wave of AI it's like very impressive and inspiring, um, and it's hard to predict, where exactly it saturates. Um, every time we seem to have hit a wall, people figure out things to get over it. But like I do think the data driven kind of Rich Sutton's bitter lesson approach. That is a lesson that we should all be aware of. What can like work with large data sets. Um, I think yeah, in terms of like what it's missing. So one issue is the interpretability of these systems, right? Um, and that's also related to how we even evaluate whether these systems are intelligent. It's very easy to like lure ourselves into the impression that we're dealing with something that is like intelligent when in fact maybe it's not, right? Because these systems have gotten so they've kind of uh, they've grown faster than we can like evaluate how good they are. So I think actually that's one reason why kind of more theoretical understanding of what does it mean to solve a problem, what is a system, uh, when has a system solved a problem or a class of problems is going to be is going to be key. This kind of so we're going to end up having to do kind of cognitive science on these systems themselves, and we haven't quite figured that out yet. I'm optimistic that cognitive scientists will do more of that, and but it would be great for there to be more crosstalk between cognitive scientists and machine learning researchers and thinking about those things. In terms of, yeah, so you asked about using reinforcement learning alongside these systems. So I definitely think reinforcement learning is going to be necessary for like combining reinforcement learning with the insights that we've gotten from training large language systems and multimodal systems. I think reinforcement learning is going to be key, and we've already seen that in like things like DeepSeek, right? Like that we're not just intelligent system, like natural intelligent systems are not just trying to pattern recognize things in the world. We're not just doing a kind of foundation model style auto encoding. We have to do things in the world. We have to solve problems, and I think that's actually a really key constraint on getting a system to act intelligently. And so I definitely think kind of tighter integrate, like kind of figuring out how to make these systems work more productively with RL systems by treating reasoning as a kind of RL problem in and of itself is a very fruitful way forward. But yeah, I think it's hard to even evaluate which ones are going to work without a clearer idea of what are we trying to do, what would it mean for it to do well, right? So yeah, and I do think that yeah, there's a lot of big open questions. It's both an exciting and intimidating time to be doing this research. I hope that there's still a role for kind of doing smaller scale, and I do think there's a role for doing smaller scale, more targeted research, and that it doesn't just come down to building the biggest system with the most parameters and then feeding in the most data. Yeah, hopefully that answers some of the questions.
Okay. Thank you. So we have a question from audience.
Can you hear me?
Yep.
Yeah, sure. I'm thinking something like in the intersection between social intelligence and the planning. Like in social action, our actions are interdependent. Like to maximize utility, we have to get to know what the other might be taking. And this kind of recursive reasoning is very cognitively taxing, especially considering the huge potential action space. And but the good news is humans can collectively construct some rules to constrain this kind of action space to facilitate the reasoning and to simplify the internal representation. I'm not sure if you have any work on this kind of problem, or do you know any work relevant to that?
Yeah, so there is some work. So like Sydney Levine, who's a colleague who's going to be joining NYU soon as a colleague of mine, Sydney and Josh Tenenbaum and Farid Cushman have been doing a lot of thinking about rules and like morality and rules kind of in the context of resource limitations. So I would check out that work. I do think so that is a very important question in my mind for thinking about how we get from just a group of RL agents solving a problem in a very unhuman-like way to somehow getting them to solve things in a more human-like way. That's kind of the I think one of the big challenges of taking RL and multi-agent RL in particular and dropping it in as a model of human social interaction is that human social interaction is very much the idiosyncrasies of human social interaction really come from our cognitive architecture, I would say, because in a way that just doesn't arise in single agent problem solving, because you have your biases, of course, and that affects like how you solve a problem. But if you then also have another agent that is responding to your biases, and you're responding to their biases, that kind of totally changes, where you're going to end up in this in like the space of possible like equilibria, multi-agent equilibria. And so yeah, so we've started doing some research very early on thinking about, okay, how can we think about, what are the cognitive biases, what are the features of cognitive architecture that really seem to constrain how people are coordinating on problems. So yeah, I think that's another area that is, I think a lot of exciting work can be done. Yeah.
Yeah, I'm really interested in the like cognitive bias you mentioned. Like, could you please give an example of that?
Yeah. So, I mean, the classic example is something like these like coordination games, so like a shelling game, where the old example is like, let's say you and I are meeting in New York somewhere. Imagine we don't have cell phones and we're meeting in New York, and we didn't agree on a specific place. Well, like we didn't get around to that, and we didn't realize that until we had to meet. Where would you go? Well, they've done experiments where like if you ask people this, they all basically say the Empire State Building, right? And so why is that? Well, it's like there's a kind of recursive social reasoning happening, which is like, oh, where do I think you would go, and where do I think you would think I would go? But then there's a kind of like saliency at play. There's a kind of like there's a bias in terms of like what comes to mind, right? Like what is like the most like New York location that we could meet? Well, it's the Empire State Building, right? And so it's like such a simple example, but it's still kind of puzzling from a computational perspective. Like I think economists have been working on this for a long time, and cognitive scientists. And so like, yeah, so it's not a cognitive bias in like the classic like heuristic and biases sense, but I do think it's a good example of how there's kind of idiosyncrasies in how our minds are organized that we seem to like leverage when coordinating with one another, maybe is the way to put it.
Yeah, I see. That's a good example. Thanks.
Yeah.
Great, thank you, Professor. Let's see if we have more questions. Okay, I have another question about world models, because it seems to me one of the key aspects of our intelligence is the way that we develop world models. And in the examples that you give about planning, one of the important part was how we develop that world model. And I was thinking, uh, the way that we started build world models is with models like Genie and Genie 2 is we try to next state prediction, and we want to give the state of the world, and then what would be the next state. And we see that these models give us good performance, but it seems to me they're not like how our brain works. And I want to ask, from the cognitive science and neuroscience, what do we know that the way that we build world models, how do we develop that world models, and what do you think we have we have to do, what is the inspiration that we have to take from that and build world models that are general? And I think because I think one of the key things about our general intelligence is the world model that we develop. What do you think is the inspiration that we have to take from the cognitive science and neuroscience to build better world models that is not huge next state predictions and can help us maybe solve some kind of problems that we cannot solve them, maybe be more sample efficient with solving some problems that we cannot solve?
Yeah, that's a great question. Right, and I think there is this funny thing that like we actually can solve any problem right now, or we can solve most problems if it's like stated. If once we set it up, we can just like run RL on it and like play around with things, and eventually we'll figure something out. But we want and so there's something. It's not just like anyway. Yeah, so I think that anyway that came up towards the end of your question, that I think is a funny observation, but Yeah, in terms of thinking about world models in particular, so part of the reason, one of the insights that I got from doing this work on, value guided construal, is that when people are not just forming a world model that, like you said, like accurately predicts the next state. Part of what's happening is that people are building a world, or building. They're not just building a single world model. They're building they're kind of constantly building world models, right? Like we as we walk around the world, we're kind of like paying attention to different things, and then like planning through that in different ways, right? And we can even look at the same situation in different ways depending on what our goals are, right? And that's kind of the point of the value guided construal model, that we're kind of building world models on the fly, right? It isn't just we're building the single monolithic world model and then like planning with respect to it. We are building world models in a kind of ad hoc way, basically. So there's this kind of like ad hocness to the way in which we are doing planning and problem solving that I think is missing from a lot of the way in which we think about model-based planning in RL. And yeah, one direction suggested by the work that I presented today is that rather than learning just like a single monolithic world model, we are learning a world model where we can kind of pick and choose components that we want to use for planning in. And so that suggests that there's like a more structure to the world model than is typically conceptualized in model-based RL. Usually we're just like, okay, you got your, we're going to kind of treat it as a black box. We're just going to have like a neural network predict the next state given the previous state. But it's like, so it's kind of related to this notion of interpretability, I would say. Interpretability and kind of manipulability, or like being able to like pick and choose things, are related, are very formally related. A thing is more interpretable if you can kind of like decompose it into like components and say, oh, okay, this part of the world model is doing this, and this part of the world model is doing this. So if I don't need this, I can remove that part and just plan with respect to that. So I think, I would say a big part, I would say an exciting direction for thinking about world modeling in RL is, how do we get the world model to a point where we can do the type of thing that people seem to be doing in these experiments, where they're kind of selectively like kind of picking and choosing their world model in some way. And I don't think maybe people are working on, I haven't seen a ton of like work looking at this particular question.
Okay, thank you. And if there is no question from the audience, okay. For the closing question, I want to ask, what's your advice for the people that are starting their career in 2025 and have these curiosities and wants to navigate their paths? What do you recommend? Which courses to take? Uh, what to do, major on, do the PhD, go work on industry, start a startup, what projects they work on. What is your advice for the people that are curious and wants to start in 2025?
Yeah, I think I would say if you're starting your journey, your academic journey in 2025 into research, so we have a lot of great tools. And we have a lot of great tools for solving problems that we know how to solve. But we don't necessarily know what we don't know. And, it's good to take classes that kind of expand your horizon in terms of like, okay, how do we even think about the problem? We think about like RL has done a great job of ML or machine learning. We can set up the problem and then we have the tools to solve it. But I think a lot of research is actually coming up with the right problem to solve, right? And a good way to kind of flex your brain to do that is like, take more foundational classes, math classes where you're kind of really thinking deeply about the components, the assumptions that are being put into a system, or philosophy classes. And so I would suggest kind of, taking philosophy classes, taking psychology classes, and like trying to really think about, okay, what are the connections between these two? How are the different disciplines thinking about the same problem? What are the gaps that one discipline is not paying attention to? Why is that the case? So yeah, I think, yeah, in terms of those types of questions, I would, in terms of like what courses to take and stuff like that, I would encourage people to kind of try to read broadly. Yeah.
Okay. Thank you. I think it was a wonderful answer. Okay, and I think we are finished. Our time is up, and I want to again thank you for accepting our invitation and your wonderful talk and being with us today.
Great. Thanks so much. It's a pleasure.
Thank you. So I think we can finish the session and have a good rest of the day. Thank you.
Bye.